Good morning, good afternoon, good evening, wherever you may be in SK land. Welcome to our third webinar. It's good to see you all virtually today. Before we get started with the program, we do have some housekeeping to take care of, as is typical. We have a code of conduct, and so by attending this webinar, you've already consented to abiding by our SKAO code of conduct. Basically, that means please be respectful to everyone else in the chat and the Q&A during the whole webinar. The chat is open to all participants to use. The chat is moderated. So if you do need to bring something to our attention, that's the best place to do that. Okay, we can't see you, so you can't raise hands, but we can see what's going on in the chat. All questions to the speakers should be entered in the Q&A box, please. Questions directed to the speakers in the general chat will generally not be answered, and raised hands will not be acknowledged. We'll answer as many questions as we can in the time allowed in the Q&A session. We might take a question after each of the talks, depending on its urgency, but mostly we'll be done the Q&A. Okay. Today's program, we're going to start with a little Q&A with our new director, Jessica Dempsey. That will be done with Naomi McClure-Griffiths. Jessica, Naomi, can you please just wave so people can see you? Thank you. Then Naomi will give us a status update, as is typical. Naomi just waved already, so you've seen her. SKA-Mid commissioning update will be done by Ian Heywood, our senior commissioning scientist. Thank you, Ian. The Low commissioning update by George Heald, head of commissioning for Low. Where are you, George? Hi. And then we'll have an introduction to SKA software by Ben Mort, the head of software product management. Hi, Ben. Great. I'll do a little wrap up at the end, and then I'll have a Q&A with the panel, which is everyone you can see online. And for the Q&A, we'll also include Nicole Cunningham, who's a member of the science operations team. So hi, Nicole. Great. Okay, I'm going to now hand over to Naomi and Jessica so they can do a Q&A and we get to learn a little bit about Jess.
Awesome. Thanks, Tyler. Do you want to just, yep, great. Yep. There we are. Hello, Jess, wherever you may be in the world.
Hello. Yes, I don't know either. No, I'm in Perth. So just got boots on the ground yesterday.
Well, welcome to the SKAO. I've had an opportunity to welcome you in a variety of forums, but I think this is the first really big public forum that we've had of a SKAO community webinar. So it's nice to have you on board. I thought I'd get to grill you here for the benefit of our friends.
Let's do it.
No, I'm not going to grill you, but first off, I just wanted to start with the obvious. What excites you most about this job, this role?
I like hard things. No, I mean I do, and this is it's a daunting one, but that's why it's so exciting. And the reason I want this job is because of all of you, the community, which I've been a part of for a very long time, the passion, the commitment, the talent, the vision that everybody has. I just want to help harness that and get it, get the science into everybody's hands as soon as possible. And in as pretty a shape as possible, right? So at my core, I'm a telescope geek, and so for me, just being able to, if not physically get my hands on it, then definitely be able to be a part of the process of building the coolest things ever. That just that gets me out of bed in the morning. So it's that's really it in a nutshell.
Super. I imagine there's some parts that are scary. What part scares you most?
The data, I won't lie. I mean, I think I think it comes from being, the telescopes really don't scare me. Maybe they should. I mean, maybe that's the bit we're familiar with, but I think it's the invisible monster in the room for me is the size and scale of the digital problem. So that for me is the one that I don't think I have my head around, at least. Just how big that challenge is. I think that's the one that I worry on.
It's a fair one. So for this audience, it's mostly scientists. Tell us about your science background. I think you've said something about my friend polarization.
Yes. Well, I mean, one of the things I will say in terms of my science is I've been unfaithful to wavelength. I think, or maybe pan wavelength. You know, when you start in sort of the instrument end of things, it's meant that, I mean, I started out at Narrabri at 19. You know, so some of my first stuff was in radio, but then, you know, going down to Antarctica and building the instrumentation, actually, really, I started in site testing and calibration, and pushing on the instruments. But I sat in submillimeter for, you know, over a decade. And a lot of the science that came out of that work was just simply a result of the instruments that I was building and calibrating. And so I've moved from measuring CMB, you know, the last couple of bumps on the anisotropy spectrum with the Akbar telescope in Antarctica. And then the James Clerk Maxwell telescope, you know, I ended up an accidental PI of a large survey. Maybe you'll be sympathetic to that, just simply because, you know, we invented a high-speed mapping capacity for our heterodyne instruments, and I had to prove that there was something worth looking at, and that's how you end up, you know, mapping the whole of the galactic plane in carbon monoxide. Um, and so, you know, it's becoming from, and that's where I also learned about big data, you know, and the joys and the travails of that. So I think, you know, doing these surveys, and then of course we had Scuba 2, and then we discovered the power of polarization. And I had to go back and understand that, particularly with Scuba 2 in the submillimeter, it was a really great complement to what ALMA was doing, because ALMA, of course, has this high definition, but the intermediate scale magnetic fields at larger scales, which mapped between the radio and those high resolution submillimeter, was what I was starting to really dig into before jumping across to Astron. And then I had to go back to school because I was like, megahertz, wow. And, you know, for me, this coming back, and now, you know, I'm just a complete geek on what we can do in the low frequency arena because it's just all quite extraordinary.
It's a fantastically broad background. I think it's going to serve you well. So I'll just wrap up with what's your first few priorities in this new role?
One of my priorities, and I guess the one that's relevant here, is I'm really aware of trying to understand how to map the expertise that's in the community and how to harness that interest and that work with how we're going to work, you know, in the day to day with the observatories on SKA. So for me, we need to make sure that that interface is as useful as possible, and that you guys are out there doing the science, right? And not the bulk, you know, monkey work and these sorts of things. So for me, this is sort of a little bit of an obsession, is trying to figure out how we do that best. And I'm all for, and the priority is making sure, obviously we want to deliver all of this science as fast as possible. I also want to make sure that we deliver the quality and we deliver trustworthy things. And so what I'm hoping our community understands is the patience we're going to have in getting it right first time, if we can. So managing a few of those expectations, and you all are willing to come and yell at me. It's okay. That's what I'm here for. But I hope that, you know, a hungry community is good, but I want to make sure that everyone knows that we want it to be fast, but it's going to take longer than what we want.
Good message. Okay, thanks, Jess. That was all the questions I wanted to drill at you. If there's anything you really want to get out there and let people know, I know you're going to be traveling the world and meeting people as DG over the next few months. But
no, just come at me. I think I really appreciated Tyler in saying, you know, that the thing I value the highest is making sure everyone feels safe in the scientific world. So I want to just make sure that especially our early career people, our up and comers, that you all feel this is an environment that you can move freely in and have agency in. So for me, that's the highest priority. So I hope everyone feels that.
super. Thanks, Jess. We look forward to seeing more of you. Okay. Tyler, you want me to carry on?
Yes, please. Carry on.
Okay. I will do
Thanks.
so. Okay. So welcome all. We'll head into the sort of main business. It's really nice for us all, I think, to have Jess on board now, and it's great to have the chance to talk to her. I'll do what I should have done at the very start, which is the important part that we really need to recognize and acknowledge the traditional owners of the lands on which our facilities are located, and pay respects to their elders, past and present. The relationship with the local and indigenous owners for the SKA is really important, and it's something that we really need to acknowledge whenever we can. We particularly acknowledge the Wajiri Yamaji as the traditional owners and native title holders of Inyari Mana Ilgari Bundara, the CSIRO Murchison Radio Astronomy Observatory, where we're building the SKA-Low telescope. But I pay my respects to all First Nations people who are in attendance today. So I like to give a bit of progress updates in terms of construction, and then I'll move into some other details during my overview talk. Progress continues at an astonishing pace. We continue to have big lifts, lifting about 3 dishes per month. So we've had 13 dish big lifts, I believe. These numbers change on an almost daily basis. There are 4 dishes operating, and Ian will tell you more about that and phase and amplitude closure. We're approaching the place of handing over the new engineering operations center in South Africa, and you can see it pictured on the bottom right. I think the fact that this is the engineering operations center gives you a sense of the scale of the telescope. And by the end of 2026, all roads, fiber, power, and infrastructure will be complete, which will be a phenomenal milestone. I like to show my clock of how we're ticking through for SKA-Mid and Low. And as I said, we have 4 dishes operating right now. That's part of what's called an array assembly 0.5, and Ian will tell you more about that. Those are shown by the blue dots in our antenna positions on the right-hand one. So every time I do a webinar, I've been updating this plot, and we have more pink squares here as assembled dishes, the 13 big lifts. And the little pink ones that you can see are the Meerkat dishes, which will ultimately become part of SKA-Mid, but are now doing amazing science. For SKA-Low, I think the big news, Elvis has left the building. The trenchers have left the site. And this may not, to the average astronomer, seem like the most exciting thing ever, but the trenchers are the things that have been digging enormous numbers of trenches for putting down fiber or for putting down the power. And when they leave, it tells you that infrastructure in the under the ground place is done. And that's a really major step. So those trenchers have left the site, and we're now moving into a different kind of era. The picture down on the bottom left is laying the mesh at one of the most distant stations, E15, we call it. So this mesh that goes underneath all of the antennas has been put down in the core and most of the way along the arms. Now this is way out on the far edge. So that shows that we're really getting to that infrastructure completion place. And we've moved into the central processing facility on site out of a temporary one. There are 69 stations, I believe, fully assembled, and 15 stations connected up. And George will tell you more about what is being done with that. Another important milestone is that the central power station is operational. It's really a drag when you have temporary power stations. Things are much less stable, so it's good to have this happening now. And in the similar kind of diagram, this one is always a little bit misleading, because what happens with SKA-Low stations is that they're in clusters. And so if we zoom in on the little central box there, those blue dots are many different stations that are all clustered together, and it's impossible to get a scale to that. But George will show you some pictures that give you a better sense of that. So we're a bit ahead with SKA-Low, as you probably all know. And we're in the place where we're coming towards the end of AA1, which is the array assembly 1, where we have 16 stations. So we will be operating that soon, and George will give you more information about that. But for me, it's just nice to know that things continue to improve and increase. So what I wanted to take a bit of time is to announce something that actually all of you did, which is in the recent production of the Advancing Astrophysics with the SKA-2 science book. This has been a book that has been in development for the last, over a year and a half, I think, coming together. This revises the SKA science case that was written in 2015 and updates it, takes it forward into the new era. The QR code on the top right there will take you to the table of contents of this book. It is an astounding array of science that we've grouped through as themes, everything from sun, earth, and planets through the extreme universe, and a good section on methods and techniques. And as I say, this is not an SKA observatory product. This is a community product because the community wrote this. To give you a sense of sort of how it breaks down in terms of the chapters, 24% or so cover the cosmos and cosmology, far extragalactic, extreme universe covering about 19%, methods and techniques, 13.5% of the chapters, sun, earth, and planets, 9.7. You can see the numbers there, but it really shows the breadth of science that the SKA telescopes, that you guys want to do with the SKA telescopes. And for me, as chief scientist, this is a really important resource because this is the resource that helps us to map out how we progress from AA star to the design baseline, and what are the science steps that we want to take to get through that process. So it gives a way to go at science strategy. Really, really useful already. This would not have been made possible without the leadership of Anna Bonaldi and Tyler Burke, Philippa Hartley here at the observatory, but really the broader team effort of all the names that are listed here, who are the editors of this book, who've worked countless hours in order to find referees to work these chapters through. And the number of chapters, 219 chapters across all of those different science areas. Not only is it a large number of chapters, I mean, this book, if you put it together, is about 4,000 pages. That's not a book you pick up and read over a weekend, but it's also a really great representation of the international nature of the SKA Observatory. And you can see the breakdown of authors across the member countries and the rest of the world that have contributed to this. So it's all available now for you to see. I encourage you to go onto archive or onto the SKA website to pick that up and start perusing through. We'll be working on highlighting some aspects of the book over the coming months, picking out figures to display and to try to highlight and bring attention to some of the exciting science that's been discussed. Now, I know that in the community, there's been lots of discussion and wanting to start planning of key science projects. This is something that's important to the observatory too, and I talked a little bit about this at the last webinar, I think, and we continue to develop the roadmap towards key science projects. Just wanted to remind people what we mean when we say key science projects. These are large projects. They need to be multi-investigator projects that address a significant science area. They're expected to be transformative in their scientific nature and to produce data of very high legacy value. They'll require substantial resources in terms of compute, in terms of telescope time from the SKAO and SRCnet. And the teams will also need to bring in resources in order to do the science with that. Now, the first KSPs will start from cycle 3 in terms of the observations, but the road to KSPs starts much sooner. So I wanted to show this as a timeline of how we expect to approach the first round of KSPs. It's important to note that there's not just one monolithic step of KSPs. We will do several cycles. They will be large projects that run for 3 to 5 years, and then we'll have another round of them. But the timeline starts pretty soon. By the end of this year, we will set out the definitions and expectations for team compositions, and communities can start organizing KSP teams ahead of a call for expression of interest, which we're expecting to put out before cycle 0 in 2028. Those expressions of interest will have a full scientific and team review. They will be the big bulk of the science that you expect to do. And they will be matched to the expected capabilities that will be in operations from cycles 3 and 4. And our capability map, expected capability rollout, is all available on the web for you to have a look at. Excuse me. From the end of cycle 0, we'll announce those expressions of interest that have been invited to a full proposal stage. And that step there will be the major drop down to the KSPs that we expect to go ahead. From there, those accepted EOIs will have tests of feasibility checks in 2031. So these will be tests of observations to make certain that things can kind of work. Assuming that they do work, there'll be full KSP proposals, which show that the teams have resources and that they can move forward. And then for those accepted proposals in cycle 2, they'll start to acquire pilot data, which will allow them to do a full end-to-end test of all of the observatory pipelines, but also their own pipelines, so that by the time the full observing starts in cycle 3, teams are ready to roll and do science straight away. So this is the proposed timeline that we're working towards. As I said, by the end of this year, we'll provide more details on how things will be reviewed, what the rubrics and expectations are for team compositions. But I wanted to give a sense of sort of reality, to give an idea of how many KSPs you might expect. So assuming that KSP time is about 50% of the per telescope time from cycle 3, that KSP proposals, we're assuming that they have leadership teams of 5 to 10 members or so, and COI teams that are at least 10 times that size, and run anywhere from 300 to 3,000 hours in the first instance, peaking in a distribution of about 1,000 hours. This is the sort of expectations that you might have for the number of KSP leadership roles for sort of member share. So telescope time will be allocated, of course, according to scientific merit, but members that are SKA members they will get time in proportion to their member share. We're expecting that to sort of drop out over long periods of time, but just to give you a sort of sense of number of KSP leadership roles for various countries depending upon their member shares. One of the things that is really important to me and to the observatory is that we build inclusive and broad collaborations. We know across the sciences that broad, diverse teams produce the highest impact science. And so this will be something that we'll be putting into our requirements for KSPs, is that your teams show diverse leadership, and that the diverse leadership across the member countries. We want the SKA to be a way to build international collaboration, not to break down by countries. And for individual countries, this is an important thing. So this plot here shows that for a generic country in any one of these share buckets where they have, say, 2.5% member share or 2.5% to 5%, this shows if you concentrated all your KSP leadership in one country, for those small share buckets, they would get on average about 0 KSPs that they could participate in. But if we spread out the leadership across all the membership countries, or all across broad numbers larger than 8, then every country participates in multiple KSPs. And that's an important thing for all of our members, but I think also for the science community. So collaborative KSP leadership is where we'll be heading, and we'll provide more information on that and expectations by later this year. So I wanted to go to the usual timeline here. So this was the last update for the timeline to science that we showed at the webinars in March. The official timeline has not updated since then, but we are seeing some pressure on the start date for low AA2 science verification. That pressure comes in a range of different forms. There's pressure, and I'm just trying to be very transparent here. There's pressure on that timeline because there was a late start to the AA1 verification. There have been some impacts of the world situation related to mitigating construction decisions. So, for example, the fact that fuel prices skyrocketed due to the war in the Middle East meant that we made some decisions to move forward all the fuel-heavy construction earlier, and that pushed some other things a bit later. There's, as we've said before about the low noise amplifiers, that's being addressed, but the ability to conduct a global sky model survey and test the lowest end of the frequency band can only start after the replacement, which will be next year. So there's a few different things here that make there a bit of pressure on the timeline, and we hope to have an updated timeline for low science verification by Q4 of this year. So in the meantime, the timeline that I showed before still is what we're aiming towards. And I'll just wrap up with a final thing. I showed this at the last webinar, but I just wanted to remind people that we have amongst the scientific team at the observatory individuals who volunteered to be the sort of primary point of call for national questions or speaker requests in countries. These are the names here. They're also on the SKAO website, and you can contact them at firstname.lastname@skao.int. And you can look out for significant changes to the science users portion of the website later this year. So I want to finish up there and thank you. And if you have any questions beyond this, I'm always contactable. And this is my email address there. So I'll stop sharing. Thank you very much.
Great. Thank you very much, Naomi. At the moment, there are no urgent questions, so I expect there'll be a bunch when we get to the Q&A session based on the information that everyone's just received. So we'll move on now to the commissioning update. So Ian, could you please share? And there you are. Hello. Great.
Yep. Thanks, Tyler. Am I visible?
Yes, brilliant. Take it away.
Okay, thanks. Okay. Yeah, hi, good morning, good afternoon. My name's Ian. So I'm the mid senior commissioning scientist in this project. I'm going to give you a brief update this morning on what we've been up to in that field within the observatory. I present this talk on behalf of the entire mid commissioning team, but also huge thanks to the assembly, integration, verification, and system science teams. So I'll begin with kind of a brief overview or recap of what commissioning is and where it sits within the observatory. So commissioning is an internal activity that focuses on tests of the science capability of the telescope using astronomical observations. So where it sits in relation to other aspects of the observatory can be seen on this kind of flow diagram here. So parts of telescopes go in on the left-hand side of this, they get built, they get assembled, they get integrated, they get verified, and then science commissioning kind of takes over in terms of the on-sky verification of the hardware itself. And once that's been validated, we move on to science verification observations on the right here. We don't exist in a vacuum, of course, so these kind of little circular recycling type icons here show that there's interaction between these various teams all along the way. But the slightly kind of less dry analogy I like to use when people ask me what I do at my desk all day, I basically use the analogy of sea trials. So the easiest way to find all the leaks in a boat is, of course, to put it on the water and take it for a spin around the bay. And similarly, the best way to shake down a radio telescope, at least in my opinion, is to basically do astronomy with it. So we take this thing, we point it at an angry supermassive black hole several billion light years away, and we see how it behaves. So at the last webinar, I'll give a recap of kind of where we were at with MID. The results that were presented by my colleague Betsy, we'd obtained interferometric fringes on a single baseline using everyone's favorite Southern Side calibrator. So this was a great moment for all of us. We'd seen galactic H1 lines visible in the dish autocorrelations. We achieved closure phase with a 3-antenna system, again observing this standard calibrator source. And we'd verified that an observing field with 2 very strong sources in the primary beam yielded the expected fringe patterns. So where we were at the time of the last webinar was basically doing basic interferometric tests with the 2 and 3 dish system that we had available at the time. So since then, the commissioning story has basically been one of opportunism, lots of teamwork and a bit of pressure. I do make the point that some pressure is not a bad thing. There is a distinction between pressure and stress. Pressure is not necessarily bad, stress absolutely is. And we briefly had access to a 4-dish AA 0.5 system in May. By briefly, I mean we had the opportunity to conduct on-sky observations for 2 nights using an array formed from these 4 antennas. You can see the diagram there on the right. We had access to band 2, so L-band in meerkat speak receivers, a maximum baseline of about 1 kilometer, and the full range of spectral frequency channels available to us, so 55,380, which is a lot. 1 second correlated dump times available, and I have to say some absolutely heroic observing efforts from our colleagues who are on site in South Africa to conduct these observations. I've never actually watched anyone observe with this telescope firsthand, but my colleagues who have tell me it's quite a daunting thing at the moment. It's lots of terminal windows, it's lots of typing commands into those terminal windows to, coordinate this ballet that all of these telescopes have to go through for people like me to get my visibilities. In my opinion, I think we made the most of it. We had 2 nights. We squeezed a lot of juice out of the telescope in those 2 nights. And I'll present to you some of the declassified highlights of these 2 nights. I'm not going to go into closure quantities in any detail. Ask me after if you're interested. But the basic property of these things is that by the property of what happens when you multiply 2 complex numbers, which is what the correlator does, you can combine those multiplications in triangles and in quadrangles, and you can get a very useful diagnostic of what the telescope is doing and how it's behaving without having to perfectly calibrate it. So amplitude closure we could achieve once we had 4 antennas. So for an isolated compact source at the phase center, the expected closure quantity is unity. These plots on the right show at the top the individual baseline responses and the associated closure quantities below, which shows that the telescope is indeed giving you this kind of unity response in the closure amplitude quantities. So that was an initial very good, very pleasing to see diagnostic. Credit to my colleague Shinichiro-san for providing this. The eagle-eyed amongst you may notice the frequency axis on this and notice that that is not all of L-band. We pick a clean region of the band, a kind of RFI-free region of the band, because RFI tends to be a non-closing quantity and we want to isolate the part of the band where we can just probe the telescope itself. A more thorough overview of L-band can be provided by this plot. I appreciate that probably not all of you are like me and you don't get excited by bandpass tables, but I think this plot is useful in the sense that it shows you a couple things. First is the kind of RFI environment, which has these clean regions, but we all know and love L-band, and we appreciate that we can't avoid geolocation satellites even in the most RFI-free regions on the planet. But the other nice thing about this plot is that it shows you the bandpass corrections across all 55,000 channels that we have access to at the moment have a smooth behavior and frequency. And the other nice thing about this plot, in my opinion, is that we managed to derive these bandpass solutions, which shows not only that the telescope is behaving itself, but we did this in this case with the full frequency resolution data using in-house SDP software tools. So this plot was gratifying for me because it's an entirely SKA-O made product, right? There's nothing off the shelf from other places that went into this. The second highlight I'd like to show you is something that I wasn't expecting when we kind of went into this phase, which is that on May 14th, we used AA 0.5 to observe the hypergiant star IRC plus 10420, and calibrated this using a scan of Parkes 1934-638. So honestly, this was completely jumping the gun from a commissioning perspective. But someone in the observatory had hatched a plan that we should observe this target as a goodbye gift for our outgoing Director General, Phil Diamond. So a major omission from this object was the subject of Phil's very first refereed paper, and someone figured, and who could disagree, that an observation of this with MID would be a nice way to bookend Phil's career. So observe it we did. We weren't planning to test things like calibration transfer from calibrators to targets just yet in the commissioning plan, but off we went. And we did learn a lot about the system in the process of doing this, and in my opinion, and I hope you agree, the quality of the spectrum that we got from this test observation is very encouraging. But yeah, we learned lots of things in terms of observing with MID and how the telescope's behaving. Chiefly that it's very important to know exactly where your antennas are. Here's a zoom of the plot here. So it's an obvious thing to say that a lot can change in 40 years, not least of which is the spectrum of a circumstellar maser. And just to prove that I didn't Photoshop this, here's the 100-channel data cube visible in the Carter visualization software. Although, of course, I have no way to prove to you that I didn't also just Photoshop this. Some final items from me then. Excitedly, the commissioning team in Cape Town is growing. So we've got 3 incoming junior commissioning scientists who will be either started already or coming soon. So Keegan has joined already. So Keegan was previously an SKA-Mid telescope operator, and prior to that, a SRAO-funded Rhodes PhD student. I've known Keegan for a while now through my Rhodes contacts, and it's great to have him on board. Keegan's an expert in visibility domain mosaicing with direction-dependent effect corrections, and also a galaxy cluster enthusiast. Suman, who's presently a postdoc in Mario Santos's group at University of the Western Cape. Sorry for poaching him, Mario. He's been the lead developer of the imaging pipeline for the fast scanning, aka on-the-fly mapping mode of the Mir-class survey. I have to confess that I was a bit skeptical that this would work as well as it has. I'm truly impressed with the work that entire team has done with this challenging observing mode and how they've managed to yield fruit with it. It's really impressive stuff. And finally, Arpan, who's starting in November 2026, presently a PhD student in Pune and Socorro. And Arpan's done some really awesome kind of forensic level polarimetric research as part of his PhD, and also has a penchant for naming software packages after Pokemon. So what's not to like? Okay, just wrapping up. So A.5 returns for more sea trials in August. I personally can't wait. We've got approximately 40 commissioning tasks identified for MID at present. So some of the big ticket items are system stability. This is crucial. Calibratability, which we've kind of touched on a little bit with the brief access to A 0.5 that the commissioning team's already had. This is calibrated to calibrator and calibrated to target transfer. Those of you who observe with the VLA, Meerkat, etc. will be familiar with this process. As I mentioned earlier, it's very important to know exactly where your antennas are, and the best way to verify this is to use on-sky observations, so a large area survey of compact calibrator sources to solve for the delays and verify the telescope's delay model. Pointing verification, I'm using the soon-to-be installed Band 5 receivers, as well as beam holography. And then something that's very important is the mid-readiness of the SDP data processing tools. So Ben will talk a bit more momentarily about the software of the telescope. And as Naomi mentioned, Low is slightly ahead of MID. So I think the data processing software at present has naturally had something of a low bias, and we need to make sure that we're not missing anything that MID needs that hasn't been included in that. So yeah, to summarize, this thing works. I'm very happy about this. I think we'll probably have an official first image coming soon. It will probably be a 4-dish image, so temper your expectations, but that will be nonetheless a wonderful moment. And I am excited, and I hope you are too. I am first and foremost a radio interferometer radio astronomer. I like radio telescopes, and I think this is going to be a good one. Here's my email address. My interactions with you needn't end right now. If you think of a question after the webinar that you didn't get a chance to put into the box or to the panel, then I'd be very happy to try and answer it for you. Okay, that's me done. Thank you.
Great. Thanks very much, Ian. Yes, I'd like to also add my thanks to Shinichiro for the work he's done on many of these plots we've seen at different talks. And thanks for the reminder about the pressure and stress. I need to keep that one in mind myself.
Important distinction.
Yes. There are a couple of questions. What I propose, Ian, is that maybe you answer Prasan's one in the chat and maybe Matthew's one on pulsars we talk about in the Q&A, because that addresses more some of the future observations we might do. That might be a good thing to talk about. Okay, next up is George with the low commissioning update. I see him on.
Yes.
Yeah,
Hi,
looks good, George. Thank you.
Yeah, great. Thanks. And hi, everyone. Really nice to talk to you all again in this forum. So I'll give the counterpart presentation for SKA-Low science commissioning and where we've gotten to. So I too am giving this on behalf of a large team, including the SKA-Low science commissioning team and our adjacent teams, AIV and science operations and system science. And so, in fact, let me begin by introducing the SKA-Low science commissioning team, which I don't think I've done in previous presentations in the webinars. So here you see the amazing team that I've got the real privilege of working with in commissioning the SKA-Low telescope. So from left to right here, we've got Sam, Julia, myself, Alec, Shivani, Randall, and Xiang. And all of us together have a broad range of background and expertise. So amongst us, we've got experience with MWA, LOFAR, NANUFAR, and other higher frequency radio telescopes as well, and have a broad range of different scientific interests that we bring to, and expertise that we bring to the project of commissioning the telescope. So I'd really like to, emphasize how much I really enjoy working together with this team, and the results that are shown in this presentation are indeed a synthesis of the collective efforts of this entire team together. So Naomi mentioned that the stations that we're working with at the moment in SKA-Low, which collectively form what's called Array Assembly 1, AA1, these 16 stations are spread over 3 distinct locations within the overall array layout. But within those 3 locations, the 16 stations are actually pretty tightly clustered, as you can see in these 3 images here. So the 3 locations are called S8, S9, and S10. Those are the 8th, 9th, and 10th clusters of stations along the southern spiral arm of the array configuration. So we had, just as Ian talked about the AA0.5 for SKA-Mid, we also went through an AA0.5 activity with SKA-Low, which I've shared the results from previously. That was using these 4 stations shown in green here. We've more recently been working with as many as 15 stations at the same time, including these 10, which are in what's called the early access mode, where they're not fully handed over yet from the construction process, but in fact, we've been using them in an early capacity. And in a slightly less early access mode, the final 2 stations comprising AA1 are shown in the pink circles here as well. So as I said, that's all up is 16 stations, which are all available at some level or another. And we've used, as I said, as many as 15 of them together. Now here, the minimum baseline is, because the stations are packed so closely, the minimum baseline is approximately the size of the station. So the minimum baseline is about 40 meters, and the maximum baseline is about 5.5 kilometers. But the UV coverage, because of the clustering of these stations, the UV coverage is still pretty sparse at this early stage. And so, as Ian mentioned, tempering expectations about image quality from a limited number of stations. Although we have 16 stations at this stage, in many ways, it's sort of like 3 stations with quite a lot of near redundancy in the baselines. So again, we have plenty of collecting area, but with limited UV coverage, as we make images, the image quality is, only just a glimpse of what it will be in the later stages of the telescope. Okay, but before I show you any more sort of advanced level data products, so to speak, I did want to spend a few moments talking about some of the more basic aspects that we're dealing with, and one of those is RFI. So this plot is a typical view of what the bandpasses of all the antennas within a single station ought to look like if everything is performing well. What is immediately obvious in this plot is a bunch of spikes which are arising from radio frequency interference. So I'm just going to highlight what those are originating from. So there is a little bit of FM radio peeking over the horizon. This is a very radio quiet site, obviously, but nevertheless, a little bit of FM radio does peek over the horizon. And other than that, basically everything else is coming from satellites. So there is a very strong known communication satellite signal that appears at a very particular frequency from time to time. And then a bunch of geosynchronous satellite emission that comes at the higher frequency ranges. So these are the kinds of things that we see already at the individual antenna level within the telescope. We also see radio frequency interference on baselines, on the visibilities between individual stations. So here we're looking at time and frequency behavior of visibility amplitudes on a baseline, a short baseline here. This is only about 120 meter baseline between two stations in the cluster S8. So what you can see here are some very clear RFI signatures. Again, FM radio at the obvious frequencies. There are some lower frequency glitches that pop in and out. Those are in fact arising from Starlink satellites, which we can identify because we know when the Starlink satellites are passing through the beam that we're observing with, and that's when those spikes appear. And then finally, what we assume, but haven't quite verified in this particular case, what we assume is an aircraft emission popping in quite strongly for a short period of time as well. Now, I should point out that this is a low frequency part of the band. And as Naomi mentioned, while the low noise amplifier issue is still being rectified, this is an area of the spectrum that we actually are not really focusing on at this point because the data quality is still limited before the LNAs are replaced. Nevertheless, this is a good part of the frequency band to illustrate some of the radio frequency interference that we will be seeing. So what do we do about it? This is a slightly complicated figure, so I'll summarize it verbally. We have a number of stages in the signal path where we can cope with radio frequency interference. Beginning at the top on the right there, we're able to, at the antenna level, we're able to identify and flag strongly deviating voltages. That is a setting that can be turned on or off. We can also blank individual frequencies that are known to be bad as well. And then later on down the chain, when the data reach the correlator, we have an imaging mode, which produces visibilities, and we have two pulsar modes, PSS, which is pulsar search, PST, which is pulsar timing. And in each of those modes, there is a unique mode for, or a unique mechanism for coping with radio frequency interference. And then later on, we can, of course, do offline flagging as well. And so, in fact, we have a custom strategy for SKA-Low. And in the commissioning observations that we're doing, typically, we avoid, anyway, the worst impacted frequency ranges in the first place. So we don't have to deal with those, for instance, those big chunks of geosynchronous satellite emission. Okay, and so just to illustrate what the typical outcomes might look like from doing some flagging, this is, again, at the low frequency range, and it's only meant to be indicative, but what you can see, if you look at the label at the top of the plot, you can see that we have the ability to apply both online flagging, which means flagging which is done automatically by the system. Again, that can be customized and turned on and off. And we also have the opportunity to do offline flagging in the standard way using our custom strategy for SKA-Low. Okay, once we've done all of that, then we can do array calibration. And I've shown some earlier results from this before, but here are some more recent results showing on the left a number of unique long baseline triangles between different stations. This is in fact only a subset. We have loads of triangles connecting the stations on long baselines, and all of those show closure phases which are consistent with the expectations for looking at a bright compact calibrator source. And then on the right we have some bandpass plots which are determined having already determined that the array can be calibrated. So Ian at least will be happy to see these band passes. So these are looking quite good at this stage for the standard calibrators that we have validated as being suitable for use for primary calibration with the telescope. From that point, we're able to make some images. I'll just reflect on the point that the image quality here is not yet indicative of what we'll achieve with the final system, but in fact is already looking quite good given the number of stations and in particular the UV coverage of those stations. But this is an example of a field around a very bright calibrator source. In fact, it was the field that we used for the first A0.5 image for SKA-Low. In this particular case, we're pushing down now to a dynamic range of about 10,000. And the red boxes here are the locations of a subset of the MWA GleamX catalog sources there above 50 millijansky. So this is looking quite good. We're quite happy with where this has gotten to, looking at the fields around bright calibrators. And we've also taken a first look at transferring solutions from a primary calibrator to a target field. In this case, what we're seeing on the right is a blink between the MWA Gleam image, which is the one that looks fuzzy, and the SKA-Low image, which looks sharper, but also missing the diffuse emission. And the missing diffuse emission there is because we've chosen to exclude the short baselines, which are sort of quite isolated in the UV plane. We've excluded those from the imaging process. But nevertheless, we're able to make a good image of the compact features in this image. And we are working towards a better strategy for imaging the full set of baselines altogether, even at this early stage. That process will become much easier later in the lifetime of the telescope as it advances to the full deployment. Okay, and then finally talking about time domain, we've demonstrated that we can make a coherent combination of stations using what's called our real-time calibration approach. We've tested the real-time calibration in an offline capacity so far and demonstrated that we can achieve coherence with the signal-to-noise increasing linearly with the number of input stations. The online mode of the real-time calibration is integrated and is being tested as we speak. And then finally, noting that we're also able to look at slower transients than pulsars. Oh, sorry, I should say on the left that that's a pulsar plot from 1 and 4 stations linking back and forth, and you can see the factor of 4 improvement in signal-to-noise in that pulse profile. On the right, what you're seeing is an observation looking at a slow transient. So in this case, a long period radio transient known from the literature from MWA. In this case, we were looking at this source to make sure that we knew how to schedule observations targeting a particular source with a known ephemeris, and also to make sure that things like, to ensure things like we didn't flag the signal accidentally. So here what you're seeing is the raw data. In a sense, it's the sum of all the long baseline visibilities. So this is not observed in pulsar mode. This is observed in imaging mode. We took the visibility waterfall spectra and added them all together for the long baselines. You can see the LPT sweeping through with what turns out to be the known dispersion measure. If we disperse that data set with the published dispersion measure, we see that everything comes good and we get the expected, in other words, it corrects the data appropriately. And we can see a very clear detection of this known LPT with even some nice, interesting structure within the pulse. Okay, and so at that point, I will leave it there, and I'm happy to take questions either now or later on. Thanks a lot.
Great, thank you very much, George. There are 2 questions. I will briefly read them out, but perhaps you can answer them offline or maybe in the Q&A later. Alec is asking about, both actually Ian and George, asking about observing SN 1987A. So it sounds like he's getting his SV idea ready. You can talk about that one offline. And Ryan wants to know about real-time flagging for PST, RFI flagging. Is it offline? Will they get a copy of the real-time data without flagging? So that may be a good one to discuss actually in the Q&A. So we might start answering that offline and we can talk about it. So flag that for, okay?
Sounds good.
Great.
Thanks.
Thank you. Okay, I'm going to throw it out to Ben for giving us a high-level view of the software for SKA. So thanks, Ben. Looks good.
Ryder.
Yep.
So Thanks all for joining. It's great to see you all here. My name's Ben Mort. It's the first time I've done one of these. I lead a team of product managers working on supporting delivery of SK software. So today I'm going to give a pretty high-level introduction to SK software, what it is, what we're doing, how we're building it, and how we want to work more with the community. So this is deliberately an overview rather than a technical talk or demo today. Those things could easily be part of future webinars, but for this session, I wanted to give an introduction to provide some more context for those possible future sessions. So the main message I wanted to leave with people today is that software is not really an extra thing we're doing to build the observatory and the telescopes. It's a core part of the activity that touches on almost everything we're doing in building the telescopes and the things you've just seen from commissioning, for example. So what is SK software? Well, the simple way to put it is that SK software provides the tools and services that take us all the way from the science ideas and proposals that people put in, all the way to the observatory data products that you'll be able to access through the SRCnet. The flow for that is shown on this slide, or a simplified version of that. If we follow the steps in this diagram from the slide from left to right, it gives a simple view of the flow of control and data through the systems in the telescope, and the major touch points with the software subsystems for running observations in the telescope. So on the left in step 1, there you've got the observatory science operations software. This supports proposals, observation design and scheduling. It turns the scientific intent and planning of proposals into a set of observations that the telescope can schedule and run. Then you go on to 2 in the flow. So when it's time to observe, internal operators use the observatory science, another part of the observatory science operations tools, along with telescope monitoring control services that allocate resources, execute the observation, monitor the system, and coordinate the telescope subsystems. It's a big part of the thing we're building at the moment. Then there's a central signal processor that handles correlation for imaging, tide array beamforming. We've had some questions about that, and time domain processing for observations where that's needed. That flows things into step 4 there, which is the science data processor, which takes visibilities from the correlator for calibration and imaging, processing time domain products, and produces the observatory data products, along with quality assessment data and metadata handling. And then finally, there's data access services, which deliver those observatory data products to the regional SK regional center network. And this is where that's where the scientists, people using the telescope, can access those data products, analyze them, and create further data products. Rather than being a single piece of software doing this, in practice, as you might imagine, this is a system of hundreds of distributed components deployed across sites and data centers, all the way from components in the field, in the deserts, close to the hardware, so software in dish pedestals, software on stations, all the way to software running in data centers in Perth and Cape Town, with also some services running in public cloud. Not shown on this slide is also another really important piece of software products, which is the support that's supporting the operations of the telescopes. So software managing engineering and maintenance tools for engineering operation stuff, platform and infrastructure monitoring and logging, data management services, all sorts of those sorts of things which the software flow stack with the flow in here is built on. So the major software systems shown on this slide and all the other things I mentioned, which are not shown on here, is actually what is supporting turning the things that you're proposing to do with the observatory into those data products, which we ship to SRCnet. So what are we doing right now? The important point is that what I showed on the last slide is not really just a design activity or something we're planning towards. It's a reality today. We're already running observations with our software for commissioning, as you've just heard from Ian and George, for both mid and low. SK software gives those people using those telescopes a relatively basic at this stage way to design and execute observations, coordinate those telescope subsystems and capture visibility, and at least for low, but soon mid, tide array beamforming data, with those functions that provided in the software being introduced, and working closely with the integration teams, the commissioning teams, and the operation teams that use those the telescopes. So the commissioning results you've just seen were built on a lot of this software. Ian mentioned that, George mentioned that, I think. The dashboard shown on this slide, so on the right, I put a picture of a dashboard as an example. This is software that's being built and rolled out for operating the telescope. It's a dashboard that brings together state and monitoring and data quality information from a set of different sources into one view to help people using the telescope. The picture you're seeing here happens to be for a low station. I think it's SA1 if you zoom in. But the same software is being rolled out for mid and being used for mid. So there's similar views for the dishes in mid and other views of the system, sort of more aggregated views. I think it's also important to point out that we are not fully full operational capability with respect to integrated data processing. I think that was touched on already. That's coming soon. We're also actively developing tools and data processing towards that, leading up to the AA2 science verification, hopefully sometime next year, with for the first data processing capabilities for being rolled out on the telescope towards the end of this year, with commissioning en route to that. The take-home message, though, is that we're already running flows through our software regularly with SKA users in the loop, so the commissioning teams, some of the operation teams and integration teams, and we're learning from that. So every observation we're running is giving a lot of evidence, logs, monitoring, all those sorts of things, data quality displays. All of those things are helping us understand and importantly get feedback from people using the telescope of what to improve. And this feedback cycle, which is starting to work very well now and ramping up, that allows it, is so critical to drive SKA software development cycles. So like the rest of the SKA construction program, software is a very large global effort. Currently, it involves 33 teams and roughly 150 people across a big range of countries, institutes, universities, and companies. I suspect people here know many people from that. A lot of the challenge is making that all those people and pieces work together in the way we build and integrate our systems. To do that, we organize the work around telescope and observatory goals. That's things we set as an observatory with the commissioning teams, with the operations teams, with the science teams. And each of those goals set out what we should improve and the evidence which we're aiming to show that works. And then we use those to drive a development cycle, something like on this slide, so we define a goal, we work out all the dependencies that might hinder or block it. We work out how to plan to integrate and provide testing of that as early as possible. We then review the evidence. And importantly, in that step 5 there in that cycle, we're continually trying to adjust and improve each time we cycle through this to learn and improve how we deliver things. In practice, it's not all perfect, but the important thing is that there are regular checkpoints in this cycle to learn and align, not just with the software teams, but across the observatory. So with the other teams that we work with, the commissioning teams that we've heard from and operations and so forth. The key idea here is mentioned on the right of the slide there, that says that that running through all this is a major theme. There's a second major theme to learning, and that's that delivering that success is not simply just handing over bits of software to be delivered that hopefully even plugs together, but is being measured. Success is being measured by working telescope capabilities, which are demonstrated and used by people. So I've included this slide to answer a question that I expect quite a few people might have. So are we building and reinventing everything from scratch in the way we build software? And the short answer to that is no. So where the community or like other observatories have trusted tools that fits our needs, we're using them, we're extending them, and we're contributing to them, providing development effort back into those tools. Examples of that span most areas of the telescope software. So all the way from the control elements. So if you remember that flow, all the way from the left to the right where there's data processing. Examples of this, we're using Tango for telescope controls. It's a common framework used by other observatories. We're using CatPoint for pointing and coordinate calculations, something used by Meerkat, using things like the Meerkat dish verification system for qualifying our dishes. And then in the data processing domain, we're using a lot of existing tools, things like DPQt and WSClean for calibration and imaging, simulations with Oscar, DSPSR for time domain processing, a lot of tools which people should be familiar with, and we're building and extending those to meet our needs. So that's also far from a complete list. Like we typically follow the principle that we start from trusted foundations and build only things that are new when SK scale or requirements demand it. So that reduces risk. It gives us software that's tested already through real scientific use cases and connects us to the communities that also understand and help maintain those tools. So it builds that shared knowledge. And our contributions to some of the community software already has also, I think, allowed others to benefit from SKA development already. So we have been putting quite a lot of effort into some of those tools, as mentioned. So our teams also bring expertise from a wide range of observers using instruments. So across our development teams, we have people from a whole host of existing facilities, some of them mentioned on the slide, things like, ASCAP, MWA, GMRT, LOFA, MEERKAT, but many others too. And we are bringing with those people, the lessons that was learned from those facilities. And then finally, much of our work, or vast majority of our work, is also publicly available on GitLab, and the QR code on the slide and the hyperlink just below it will take you to the main SKA repositories where you can expect and follow that work. Just a sort of minor health warning, not every repository is mature, stable, or supported at this stage. Many are very far from that, but the engineering and tools are there that we're using are there and open to inspect if you want to do that. And the final message here, I guess, is that we're building on and contributing to and extending trusted tools, and we're doing that because it's good engineering practice, not just a separate activity, and it's fundamental to how we're doing everything. So I wanted to finish with a slide which touches on how we work with the community. So this is an area that we want to improve on and extend over time. I think we fundamentally believe that scientific expertise and understanding is central to how we deliver useful software all the way through the flow I showed on the first slide. And it's not something that we just want to add after software is finished. That would be bad practice. There are 3 strands to our approach for this. Firstly, for certain defined modes and pipeline questions, we're already working with external experts, and external experts are working with some of our SK teams, those in science operations, for example, working to assess what can be adapted, adopted, and used for various areas of development. Secondly, we're working and building a working relationship with other observatories. This goes beyond the list of observatories where we have developers, so also including like NRAO, for example, working on interoperable processing, shared more performant data formats, reusable algorithms, and rather than reinventing the same things at every facility, trying to work on how we have a more concerted global effort on that. And then third, we're planning on introducing more technical groups around defined problems with clear outcomes and practical ways to contribute. And while we already work with experts in specific areas, and we already have access to a number of people in our development teams who have built quite a lot of the tools which people have been familiar with, or projects running on various telescopes, over time we realize we need to broaden this out, but we want to do it in a careful and structured way. So the participation model for this is still developing. I don't want to give a vague invitation today that go nowhere, but instead we'll share more information on topic, scope, and participation details as that model develops. So 3 simple take-home messages to conclude. So first, SK software connects almost every part of the telescope and observatory. For scientists, it gives the path from the science ideas you put in, the proposals, through the observation and then to the observatory data products that will deliver to the SK regional sector network that you'll have access to. So it touches on pretty much everything. Second, early end-to-end flows, and some of the use of the telescope is already running on mid and low, real observations with real data and real feedback from the people using the system, which is greatly helping our software mature and improve. And third, we're trying to build on community foundations with expert radio astronomers working in and with our teams, and we're learning and trying to learn more from people who are using our system as part of the development. And finally, this talk is an introduction, so I really want to know what you'd like to know about next, really, for future webinars as well. And that concludes. Thank you very much.
Great, thanks very much, Ben. There was one question which we will leave for the Q&A, because I think it's something we all need to maybe think about, from Richard, and I've put it in the live. Okay, so moving on, I'm just going to do a little wrap up here. Okay, so we will be at future meetings. Always put a slide up like this. If you're attending any of these meetings, please seek us out. We may be giving talks, or we may be attending and attending with a stand or something like that. We'll be at the ERSI Gas meeting in August. We'll be at the EVN meeting in September here in Manchester. Swiss SKA Days in Neuchâtel in late August. And the precursor workshops for H1 and Continuum Fission Sparks later in the year. So if you're at any of those meetings, please seek us out and have a chat to us. We have a poll which we're going to run now, and it's going to run all through the Q&A. So you can please just take your time to read over this, and you can give multiple choice answers. We'd like to know what you would like to hear in future webinars. It's just been touched on by Ben. He wants to know more. We all want to know more. So there's a whole list there. Please read through this list in the poll, and we'll come back at the end and see what people have to say about that. Before we move on to Q&A, I just wanted to provide my also thanks to everyone who contributed to the book, the authors, the editors, and also the reviewers. That's very important. And a massive thanks once again to Anna Benaldi for leading the charge here. Okay, we're going to now go to the Q&A session. We've had some questions we'll answer live. First, we want to talk a little bit about the plan for observing pulsars with MID. What's the timeline there? Ian, could you please say something about that?
Yeah, so the current project plan gives us a boresight timing beam for MID with AA1, which is going to be about November of this year. And then following that, we'll get subarray timing beams for clusters of antennas for the higher number array assemblies. As we get more antennas, we'll be able to subarray those and get more boresight timing beams.
Excellent. So all going well towards the end of the year.
That's the plan.
Yeah. Fingers crossed on that.
Hopefully, end of the year we'll have a pulsar observation with MID, which will be a great moment. Yeah,
that would be fantastic. There was a question about RFI flagging for pulsar timing with low, and George, and even anyone else who would like to have a go at that. George.
Yeah, happy to. I'll mention that I've been able in the meantime to backstop my own knowledge with a bit of info from the Brains Trust. So thanks also to Andrew Jameson for helping us to be aware of the exact details here. So there are a couple of different parts to the answer here. So first, like I said, we have the optional ability to flag data at the station level before it arrives at the correlator beamformer. As I said, that's optional, but is important because once you've formed a tight array beam, of course, you can't then flag the RFI that went into the formation of the tight array beam. You can only flag at the level of the resulting product, but that is also an option as well, optionally. And so that's at a couple of levels actually. So it can be done, real time optionally, real time in the pulsar timing mode. And then there's also some optional requantization that can be done of the resulting data, and I believe that can also be optionally flagged as well. And so I think perhaps any further detail on the various flavors of pulsar timing data that can be recorded is probably the subject of a future presentation. But in brief, I'll mention that we've so far in commissioning been able to detect known pulsars with single stations by themselves, with a tight array beam, as I showed. and also in a re-quantized version of pulsar timing data as well, which has the benefit of allowing us to record for a longer period of time without filling up a hard drive. And so, we've been able to do multi-hour scans on known pulsars to monitor, long-term system behavior and so on.
Great. Thank you, George. I don't know if Orion is still on, but if he has a follow-up, I'm sure he'll write it in. We may be off to the next meeting. We had a question from Richard Dotson about how we're going to combine multi-day observations and integrate, considering that we won't have access to the raw visibilities. I see Ben nodding away there and others on this call as well, because we're all used to combining our visibilities to make these multi-day observations. So I'm going to open the floor to who would like to have a go at addressing that. Ben, Ian, anyone else? Naomi?
I can have a go from the science
Nicole,
operations
yes.
side.
Sorry, Nicole, because you didn't speak, you're hiding on the bottom of my screen. Please go ahead.
Obviously it's an interesting question, and how we go about tackling this. So these would come under project level data products, which are, as you've said, a combination of multiple individual data products over a 4-hour window added together. So in the first stages of science verification, and we will be doing 4-hour observations that won't need this combination, but how we combine those into these PLDPs is something that is very much on our radar. And we have there's a lot of community experience on this from large surveys, and we've had discussions with some of those groups. And as has been mentioned a few times with these technical working groups, this would be a topic that could go into that, of how taking community experience on that, if we go down paths of things like gridded visibilities, or with compression, or depending on how many hours they are, if there's a possibility of holding things in SDP, and doing that combination together. So it is something that is very pertinent for us and is ongoing. And we obviously want to deliver something that you as the community would trust in those PLDPs.
Okay. Does anyone want to add anything to this? Because I know this is a really important topic. Okay, I'm going to say that it's being answered, unless Richard's online and wants to have a follow-up to that. Okay, so we have a question from Cameron, which I've already said we'll answer live so people can read it. Are there plans for SKAO to share with the astronomers best practices or tools for handling large data products? And I'm not going to read the rest of the question, but Ben, is that something you want to try and address?
I mean, the short answer is yes, but this is principally through SRCnet, to my understanding. So we do make SK software available for use there, and the tools and the stacks for that. But in principle, but the main route, to my understanding, is that this works is mainly a function that's done with SRCnet. That doesn't necessarily mean that SRCnet's going to provide answers for everything there for every tool that everyone's using, but certainly they'll do and will do what we can to support this as best as possible, because we realize it's a big problem, and that is part of the intention for why we're providing SK software itself also to run on the SRCnet compute nodes. I don't know if anyone wants to add to that.
I can just add in the first stage of science verification, this is one of the big reasons why we'll have some resources available on SRCnet for users to handle those bigger data products. We will deliver things like visibilities in those first stages of science verification. And then, as we go forward, or as Ben was saying, the data will be accessed through SRCnet. In those first stages of science verification, you will have the ability to download data as well to work on. But if you need, if you may need more resources, or for those bigger data products, there will be a call for resources on SRCnet in that science verification idea submission process.
Okay. Before we get on to the next questions, Richard did have a follow-up for Nicole. He wants to know if multi-epoch is not on the near-term path. So which cycle is likely to be tested for doing multi-epoch observations?
So that is on our rollout of modes on the website. I'm just trying to find that slide to give you the exact date of when.
All right, do you want to come back? Oh, got it.
Yeah, so for low, PLDP generation would start in cycle 1.
Okay, excellent. Thank you. So I also put another questions pushing through there. This is one for you, Ben, I believe. With regards to the software, is there a plan for community inputs from astronomers, and will this be solely through SRCnet? You sort of touched on this already.
Yeah, I think I touched on this in the slide. So I mean, I can say this. I can perhaps elaborate, or so the answer is yes, effectively yes. We are already working with some members of the community, and that's mainly an activity that's happening. And maybe Nicole wants to say something about this with science operations and community members to analyze, what software already exists and what we can learn, what we can adapt, and what we can adopt and extend. We would like to broaden that to more cases, but we're trying to work out how to do that in a way which is structured, effective, ties well in with the timelines, so that we get the best out of that on both sides. Because we're also already using quite a lot of community software as a starting point for a lot of SKA development. We're also already looking at what people are doing now. Direct connection between software and the community is something we're also exploring, looking at, but the model for that needs more thought, because we're also in the moment buried in delivering and rolling out critical telescope functionality, which is supporting commissioning, and so balancing those two things is obviously important.
Yeah, I can follow up with that, with the community aspect side on the SRCnet. So we had a team of what we call SRCnet project scientists. So they are experts from the community in different fields, and they went through a process of defining what we call detailed science verification cases, which were the types of things we plan on doing in science verification, so that we could look at those and understand what types of workflows and software would be needed for the users on SRCnet. There will be a public document of that work done, which will include the kind of software packages we are planning to include on SRCnet in those first stages. And I mean, I really agree. Part of science verification will be the users, getting on the system and giving us that feedback that this, we need this software, or this software is not what we want. So having that feedback loop during science verification, and that document, and getting feedback on that ahead of science verification on the software, the types of software we are planning to have.
Great, thank you. So there's a question from Julian. Are the data formats coming out of the observatory for the different data products already known? Or if then something we can discuss in a future webinar. So Nicole, maybe that's for you again.
So yeah, I would say if you go on our science users website, there is a document that is called Science Data Products, and that details the breakdown of the different observatory data products we plan on delivering.
Good. Maybe you could stick that link in the chat if there's time.
Yep.
Nicole, be great. Okay. So that's already done. Naomi's answering a question from Pianat. Do you want to say anything about that, Nicole? Sorry, Naomi. I've now missed the answer. There we go. Yes. Yes, could you please talk to that?
Yeah. So we have a question about does it still stay that the SKA will only provide users with calibrated images and not raw or calibrated visibility cubes, but pointing out that it would be useful to have workshops and tutorials on data format and related software. And that is the objective behind the science verification stage of the observatory plan, is to give people time to interact with those tools, understand how they work when they are at a stage where the data quantities aren't enormously large at AA2 science verification. That's to give the confidence to understand how the data products are produced, because the visibility data in the steady operations is just too much, too large to provide broadly. And Nicole or Ben can say more on those things.
Would either of you like to?
Sorry, I was just finding that link
Oh, okay.
for the data products. Yeah, I mean, I'll just add that, as Naomi said, in the first stages of science verification, this is the reason we are delivering visibilities. They would be calibrated and averaged visibilities during those stages to build that trust with the community, so that they can run their own pipelines on things and make those comparisons and give us that feedback.
Excellent. Thanks, Nicole. I think Bile had a follow-up on the maybe on the time of arrival. Are they time stamped? Is that? I guess that's the question.
Oh yeah. Okay.
Yeah.
Yes. So I'll just mention, like I wrote in, I provided a response to the original question there, which is that we've done a lot of monitoring of known pulsars so far, mostly in single station mode, but also in tight array beam mode as well. But that's, as I said in the response, has mostly been to this point about data quality, really, and consistency between stations, more so than times of arrival just yet. But that will come. Perhaps the thing I could say here is that we don't have the final clock system yet with SKA-Low. That will come a bit later, and I think that the detailed time of arrival monitoring is probably going to most effectively happen when we have the final clock system. We can already do it now, but the clock system will change during the commissioning process here.
Great. Thanks, George.
But the data are time.
Yep.
I should have answered the question directly. The data are timestamped. Yeah.
Okay. Julian has a follow-up. Nicole is asking specifically about the formats for the data products, not just what they are. Yep.
Yeah, sorry, I misunderstood that.
Yes.
So in some cases we don't have the full definition of what the formats will look like. We're still developing those, and they would be shared with the community as soon as we have those. Maybe that is a topic for a future webinar that we should plan.
I can probably add a little bit to that. So in the first instance, we're expecting formats, for early on, formats to be what you're all familiar with. So we're not going to be giving like strange new things that you have to adapt to. And in any cases where we provide converters to make that easy. That doesn't mean that won't change over time a little bit. We are working with other observatories on more performant, scalable formats. So at the moment, a lot of that's focusing on visibility data, which is not a core thing, but it's more internal. So working out what measurement set version 4 looks like and how that format's specified and how that scales and things like that. But that will certainly extend to other formats as well. But in the first instance, yes, expect things which are familiar but as the observatory evolves and the data products get bigger, we will be looking at that more carefully. But as a cross-observatory effort, not just unilaterally with SKA. And yes, we can cover more on that soon, I would have thought.
And now we're going to go into Q&A session. I'm going to stop sharing for that. Ben, have you had a chance to think about some of the stuff on the SDP? Because we might get into that.
Well, I'm going to go to the GitHub one then from Sean. Okay. So that says, does the use of SK GitLab extend to the engineering tool software needs of the SKO, or is the GitLab repository primarily used for DSP software systems? Our GitLab actually includes everything. So with the exception of a few private repositories where there's commercially sensitive code, like where we're working with vendors, it includes everything from the control system, the infrastructure, developer-facing tooling, like every part of the telescope. If you look in there, there's subfolders for pretty much all of those major systems I had in the diagram. There's a lot of other things as well. And each of those contains repos, multiple repos for each of those components. There's hundreds of repos in there. So it's pretty much everything. If you had a more specific thing, I'm certainly happy to help. Like the part of the reason for drawing the flow diagram is that the top level structure is organized around those large subsystems to a large extent. So that would help navigate the repositories. I don't know if that answers your question. On the SDP development, getting involved in detailed step at this stage on individual particular algorithms. So looking at performance improvements in given images, for example, we don't have a very good model for that. I will say that we're not rolling out GPU hardware in the first instance because the current economics has not really let us do that. The GPUs these days are not particularly favorable for cost reasons, given the big takeoff of GPUs for AI. That doesn't mean this isn't possible in future, but I think the best way I would encourage you to do this for now is if you can demonstrate good working performant codes that are clean, we will be looking at them. We'll be assessing them, and we're very happy for you, to work with you to do that, and work with our science operations group as well to assess them from both a science perspective and operations perspective as well as the coding perspective. I don't think we have an easy model where you can pick up tickets. In practice, we're running between 5 and 6. It changes a little bit. Development teams working on SDP, working in fast iteration cycles, trying to identify what the most critical steps are on a short cadence, and then picking them up as it's going. It's very hard to get involved in that at this stage, but certainly if you're developing new approaches, do get in touch, and we'll work with you to review them and see if we can learn from that and adopt it for our system. There are definitely constraints of running an integrated SDP capability, which makes some of that perhaps a bit more challenging. The other opportunity there is to get involved, I guess, more in the regional center development, or once the data is there to test some of that there with us, I guess. I don't know if Nicole, you want to add anything to that? Your team, I know, has been more involved than mine in this sort of thing.
I mean, I guess just to say, some of the external expertise and groups that they've been developing with MIA class type is probably a good example of that. Has been very positive, and there is the plan to extend this, as you said in your slides, Ben, to these probably in a more structured way, which would come with the technical groups, but that is still being in development and would be, I think, communicated when we have a more structured plan.
Okay.
Was there a question I'm missing? Because I'm sorry, I'm trying to find things in chat.
I think that was pretty comprehensive from both of you.
Good.
I don't recall, you put up your contact details in any of your talk, Ben?
No, I didn't, but I'm very happy to give it out. I should have had it on my last slide.
Yeah, okay. Seems like Keaton would maybe like to talk a bit more about that. Great. Okay. So there's also a question I can't find right now, but it's one Naomi's going to address from Mamta on the commissioning.
So we have a question from Mamta Pommier about taking a look at commissioning data. At the moment, the commissioning data is in a pretty raw state, and commissioning is an internal activity. But the time is rapidly approaching where science verification data will release out to the community. And when we do that, that's the chance for people to get in there, look at the data, look at the pipelines that have produced it, test it against your own favorite imager or whatever it may be at that time, and compare those in order to really get a handle on how those data are looking.
There's no other actual questions at the moment. I did prompt George to talk a little bit about what software is currently being used in the commissioning, because there was a question on that. So, George, you say something?
Yeah, happy to, Tyler. Yeah, so this is in response to Martin's question about the distinction between how much of I'll speak just for SKA-Low at least, how much has been done with SKA software and how much has been done not with SKA software. I'm slightly reiterating what I typed, but the approach that we've taken is to gain familiarity with the system using legacy tools, and then use that as a benchmark against which to compare the results coming out from the official SKA software. And that's been extremely successful for the primary calibration of the array. So for things like, rudimentary things like delay calibration and bandpass calibration, flagging, averaging, all of that's been done very well. So we're able to use the SKA tools now for those tasks. When it comes to the self-calibration, I'll say two things. First, imaging, although it's a useful diagnostic at the end of the calibration process, is not one of the main drivers for the commissioning process at the moment with the limited UV coverage that we've got. We do it, obviously, but it's not, achieving high quality images is not one of our top goals right now. So it's largely been done as a manual activity. And we're also at the point still of really making sure that we understand the process more so than testing the SKA software itself. But as I said in the response, we are actively working with the development teams. I guess the last thing I would just reflect on is, just reiterating a point now that Ben made, which is that, of course, the official SKA software, is built around a lot of tools that are used in the community anyhow. And so, it's the pipeline structure and so on that we're testing. But a lot of the component software, DPCube, WS Clean, whatever, like we know how those things work, and we trust them as individual components. So I'm not sure if that helps, Martin, but I think basically it's a bit of a developing process where we're always bouncing back and forth between testing performance with things that we know, while then also validating the software performance at the same time. Now, of course, maybe the last remark is that, of course, this won't work anymore when we get up to like the really big scale of the array. That, then we won't be able to use legacy tools anymore because, for instance, I can't run Casa on my laptop anymore to do data processing when we have 68 stations and more. So this back and forth procedure that I'm describing now really only works at the early stage when we just have a small array assembly to begin with. But that's how we're handling it currently.
Webinar newsletter, the slides from today and the recordings and the newsletter will be available soon on our web pages. You can see the QR code there if you want to download it. The next webinar will be in November. I just wanted to finish with one final comment on the book. Naomi already talked about the book. I just want to give my thanks for everyone who contributed as authors, editors, and reviewers. I know there are many of you out there. And again, a big shout out to Anna for leading the charge on that. This is going to be a great resource for us getting to the design baseline, which is what we all want. Okay. I think that's it. If there's nothing else from anyone, I will say goodbye, and the panel will say goodbye, and see you next time. Thank you very much.